Hello everyone, today we are in another math lab talk, and today we have Saptarshi Halder from math first year, and he is going to talk on chaotic dynamics on Riemann surfaces. His interests are in analysis, and over to you, Saptarshi.
Okay, thank you so much for the introduction. Hello everyone. So today I am going to talk about chaotic dynamics of the Riemann sphere. So let us first define it. So I will keep the talk very basic. I will not do the proof very rigorously because this will make the talk little bit technical. So I just want to discuss some of the results, some theorems, such that we can motivate to take up it as a subject of our interest. Okay. So we first define the this is. So on C hat, so we define C hat to be the C union at infinity. So what is this? This is the basically just the complex plane, and we are compactifying it with infinity. So it is just a one-to-one compactification of C. Okay. Now we have Mobius maps. We know about Mobius maps. So it look like this E where AD minus BC is not equal to 0. So you can relate with this with PSL to C, of course. So we know that this is a holomorphic map from C to C. This is a self map. So this is holomorphic. So now what we do is that further we can relate it with C hat, because for a chosen value of Z it blows up. So we can say this from C hat to C. Okay. So now we define the rational maps. So basically we define it by Rj. So what is this? This is Pz divided by Qz. So these are all polynomials. So these are our polynomials. Now so it is an this is also an holomorphic. This is also holomorphic. We define this to be holomorphic. So this is holomorphic. And it's an automorphic. Later we will see that the set of all possible holomorphic automorphism from C hat to C hat are precisely those rational numbers. Now we discuss something routine which we know from our class notes. So the stereographic projection. So this is the definition. The extended stereographic projection from phi from C infinity to S. S is the just sphere we take defined by the mapping. Phi Z to be this is where phi infinity So what we do is the following. We have this complex plane and we draw a sphere. So this is, we all know, we take a point here and we have this north pole, so we join them. So where it cuts from the sphere, we define this point to be this point. So whenever we go to infinity, so this will map to this north pole. So this is the description of what we are doing here, this map, the stereographic. So one thing we need to do is that whenever we are in C, in the complex plane, we can have the Euclidean metric. The Euclidean metric tells us everything. But as soon as we compactify with infinity, we can't have that Euclidean metric. We have to define something more. So this is that is called as chordal metric.
Suppose if I'm not mistaken, probably that can't always be automorphism, right? Is it by using like 1 by z square or something like that?
Yeah, but we will show that for a given degree where it is non.
So what is automorphism? So self holomorphic maps, right?
Yeah.
Inverse is also holomorphic.
Yeah.
So then automorphism CKL is precisely PSL to C, right?
Yeah, it is automorphism from PSL to C is are the PSL to C. But what we will do, we will give some restriction on the degree of this rational groups. In that sense, it will behave like
so
a.
first of all, then this R is not automorphism always, right?
No, it's not automorphism. I have told them that we will impose some condition on the degree to be holomorphic automorphism. There is something we will come here. So let sigma be a metric C hat such that this is equal to C. So this is precisely. So we call this is the chordal metric. So this is nothing. This is a name, just a name. So from where it is differ from the usual Euclidean metric is that we have now C hat. So we have infinity with us. So we can't define that metric here, the Euclidean metric with infinity here. So we define it like. So every time in the when I use some definition of some metric or some distance, we will be talking about the chordal metric. Okay. So we move it further. So now we define the dynamic of physics. Okay. So we have X, a space. Let's have a space. So maybe you take a set and do it may be a topological space, but it will be more. We will give some more conditions on this X such that it can maybe it's a matrix space or anything. So as of now we have X as space and a function from X to X. Okay? And we are interested to know these types of things. This is just composition. So we denote it by this. So why it is dynamic? So why it is called dynamical system? So we take a point P and we give this function on that point and we get a point. and after that we compose it with same f, and we get another point. So what is doing here? That we have P, we have gone to a point FP. Maybe this point is the same as this point, but may not be. Okay. So we have this. So it kind of giving a rule to see that how this function behaves on certain points. The iteration of the function gives in the on the certain points. So maybe x we can choose a topological space or maybe a metric space. Whenever we take is a metric space, it will be a nicer thing. Okay, we can have the distance between them and so on. We can have a notion of distance, as well as the x can be taken as a smooth manifold and so on. So in that scenario, that dynamical system is called the smooth dynamical system. So there is so I want to say that it depends on this space x. Now we have the so we come to our thing is that so we have holomorphic dynamical system. So X is complex manifold. And F from we take F from X to X meromorphic. So one can define this that's it. So we will restrict our today's talk in X to be C hat. Okay, so this is the simplest one-dimensional C manifold. This is the simplest one-dimensional C manifold. Okay. So that is the thing. What we do, we define certain things. So this is some definitions. To study the rational dynamics on the Riemann sphere. Definitions. So if is from C hat to C hat, so theta be a periodic. So what is mean to be periodic? So we iterate f on this zeta. Sometime after a certain stage, maybe n times iteration, we get back theta. Okay. So zeta is a periodic point. With the smallest iteration after which we get back theta is the get back zeta is the thing we call the period of this point. Now, So we have introduced a term called multiplier. So what is the multiplier? F is a meromorphic map from C to C. Now zeta is the periodic point with the minimal period k. So whenever zeta is not equal to infinity, we define the multiplier of zeta to be the we have defined lambda to be the multiplier of zeta is equals to that k times iteration of a and the derivative of that this thing at computed at zeta. Okay, and whenever zeta is equals to infinity, we define a function gz which is 1 over f 1 by z. So we compute g prime 0 z. So these are the multiplier of now. So we have defined these three terms which we will use in our upcoming time. So the periodic point zeta is called attracting if we have this condition that the multiplier of zeta is bounded between 0 to 1, and super attracting if the multiplier is equals to 0, and the repelling if this goes. So these are the these three things we will need in a later. So now, so we introduce another thing which is very important. So this is called the current. So we start for and super attractive point. Periodic point. We define basin of attraction. So we denote it by this set of So what is the basin of attraction? So we have the attracting and super attracting periodic point. Now the basin of zeta is the set of points that belongs to C hat such that whenever we add f on z repeatedly, it goes to zeta as intending to infinity. Okay, this is simply called the basin of. So now another thing I want to define before going to the motivation of what we are doing. So till a point, we call a point zeta to be a critical point when for a meromorphic function f, the f is not 1 1 at the neighborhood of e. Okay. Then we call zeta to be a critical. This is just the terminology and what we define. Okay. So we go further. Some another terminology I want to introduce. Valency. So the valency if at is gauge if so the valency of the function f is nothing but at 0 is the unique integer k such that this limit exists, and the limit is finite and non-zero. So this is another thing I want to define. This is the valency. So we denote it by Vf of z0. So we have talked about basins. So we just make something to emphasize that term of basin because it will come many times in the remaining part. So what we do, we just take an example. This is Lz equal to z square. Okay. Now so we can change of course we can fz equal to z square. So we can give a certain transformation so that infinity goes to 0 and 0 goes to infinity, or maybe not that we can change the role of 0 and the infinity, because taking 1 by z square will make infinity to 0 and 0 to infinity. 0 is going to 0 here and the infinity will be that time infinity will be goes to 0. Okay. So what we have? So this basin of infinity, and we have f, that f, basin of infinity. So you can observe that here any point which satisfies this thing when we iterate this map on these types of points, this set, it will go to infinity for repeated iteration. Now we have this map actually 1 over 3. So this basin of 0 and this also is 0. So basically what are we doing? So here it is going to infinity. Now if we consider this set strictly less than 1, then after many time iteration it will go to 0. So basically these diagrams tells us that once we have a map from we have some map F. So we have this basin of infinity to the basin of infinity. We have these types of change of coordinate which take infinity to 0 or change the role. So we will also then we will have this map basin of 0 goes to basin of 0. So we are fine with it. Now we come to our one of the main topic of discussion, the Fatou and Julia sets. In the when we do numerical analysis, we know something called Newton method. So what we do, we have to find the root, where the root actually belongs, just to locate the roots of the polynomial. So it is the same thing we are going to do. So we have a map F. We will define for rational map later. So we will first do this F for a F function. So function from maybe R to R, suppose R to R. Suppose we define Newton map to be the following. So we define this the Newton map. And we can observe that equal to so at a point P where this vanishes actually is the root. So we can call that P to be the root of F. So it's equal to 0. We have this curve. So if we know about the Newton map of certain function F, then we can use those approaches. The thing that the basin or the super attracting point, so we can come to a conclusion that where is 0 occurs, where is 0 is. So with keeping this on mind, what we define is that so we define it for complex. If from some C to C, so we have if mu from C to be So we have this 0. So observe that whenever f is a polynomial, we have neutron map to be a rational map. Whenever f is polynomial, we have the neutron map to be a rational map. So our main aim to find the zeros of this polynomial. So without looking where the zero are, so we look on this, in this map, rational map, and we study the dynamical system of. So as this correspondence holds, if we can study this, we are studying. Actually, we get some information about this. So this is the motivation of doing this. So another thing. So why they get? So that is set of that. Is that? So we have defined the basin of attractions here. So one thing a natural question we can ask is that the union of the basin of attractions. So there may be some more than one basin of attractions we have observed there. So one basin was at infinity and one basin was at 0. So the union of so one may tell that the basins, if we take the union of the basins, we will get completely CF, but it's not. We can see that example with that example as well. The one basin was at infinity, one basin was at 0. Now, if we make the union of these two basins, we are missing something, which is mod z equal to 1, the S1. So at that point and that circle, nothing is attracted. Why we will see. So this is possible. So here a question asked by Stephen Smith. Can we find arbitrary? And we have from that if we can put the NF basin of neutron map. So basin of attraction is forward orbit contains okay. So the students will ask this question that if we take a arbitrary f and we can talk about its neutron map. So so we look at the basin of attraction. So and he asked that it is can it be possible to find such f such that its basin of attraction, the forward orbit, actually the forward orbit, the iteration set, okay, by iteration with the set we get is a full measure. But sometimes later back it was answered that it's not possible. We can't have these types of set. So which give us some motivation to have that maybe we find a f such that the union of the basin of the attractions is not only not the C, and which is not attracted, it has some positive meaning. Okay, so this is the thing. And now introduce so we denote it by HR. So with respect to the rational plan R, we denote the fact set by FR. So this is the largest open set C on which R, and we know this notation, forms equicontinuous. So what is equicontinuous? We know about the continuity at a point. We know the uniform continuity as a whole set. So what is equicontinuity? So equicontinuity is just basically what we do is that we have some we make some uniformization on the functions we have considered in this set. So this is equicontinuity. So you can have the mathematical, you can have that even x are greater than 0, there exists delta greater than 0, so that with respect to that mentioned, okay, this x y less than delta implies sigma of x y. So this is just the equicontinuity. What is equicontinuity? So for all n, we look at the nth iteration of R, and we have whenever x and y are pretty close, then the nth iteration evaluated on that point are also pretty close. Okay. So this is the basic thing of the equicontinuous thing. So the Fatou set of R is the largest open set in which these forms are equicontinuous. Okay. Now we can have a picture to illustrate it. So we have this. This. So we have a point x here, y here. So we iterate. So we have seen that it goes to 0. So also this. So what we do is that here it is maybe somewhere it is R. Maybe x. So x and y are pretty close here in the mod z equal to 1 inside the mod z equal to 1. So we iterate the rational map. So we iterate the rational map, and these are eventually become very close to each one. And at a certain stage, or maybe at infinity, it goes to 0. It comes to 0. So this is the thing, and so we can have the we have used the terminology 10. So here the dynamics is very nice because whenever we have 2 points and iterate the same map on that our rational map, so we get closer and we eventually come to at 0. So the dynamics here it is 10. So it's nice dynamics. So here it is also because even if we take these 2 points and it blows up to infinity whenever we use the map z equal to z square, z goes to z square. So the dynamics here and here are nice, but not the dynamics here on the circle is not nice. So we will see why it is not nice. Here it is. Before going to that, we define Julia set of R is equals to just complement of it. So this here and here the dynamics are very good, nice, but on the circle we will see and conclude that this circle is precisely the Julia set of that rational. The R is equals to R of Z is equal to. So let us do it. So we have S1. So we know this. 0 is identified with 1. Now, if we have theta, this will go to e to the power 2 pi I. Basically, what is doing happening? So theta goes to 2. Theta goes to 2. Okay. So So we take to understand it clear, we take the binary representation of. So what is that? Theta is equal to simply 0, A1. So this is entries from 0 to 0, 1, 0, 1, 0, and it goes. So one can find like 2 plus 2 square. This is just the binary representation, nothing. This is theta is A1. So A1 into A3 here belongs to some 0 and 1. So what we do is that A and so whenever we have e to the power 2 pi I theta and e to the power 2 pi I 2 theta, we look something different because if x and y were pretty close, so these representations will be pretty close. Maybe after 100 or 1000 terms it differs. But when we iterate the rational map R more than that time, you will get just opposite. Whenever it is 0, it will give 1. Whenever it is 1, it is gets 0. So after 100 or 1000 times of iteration, we will get those two close points on mod z equal to 1. It's no longer close, they are totally antipode. Okay, so here as we go to infinity, we are not going to get a nice dynamics. we are getting a chaotic dynamics. So here, so we conclude from here, we can conclude that J of that and R, the R is our square. This is precisely and you can observe that this union makes the whole C intact. So this is the Julia set. So what we can discuss like this. So the so if so we can study the topology of the Fatou and the Julia set. Okay, many topological properties. Okay, measure theoretic properties can be studied. Connectedness, compactness, many things can be studied. So these are some little bit technical things. So we are not going to do that here. So we study just we just introduce the polynomial dynamics once more to emphasize the fact. So Pz is so when z goes to infinity, observe that this term no longer dominates. This term going to dominate. This Pz whenever z goes to infinity, so this will dominate. So we have that basin of. We can talk about the basin of. So open set of points. This is the open set of points that converges. So what we have discussed so far is that the nice dynamics on the Fatou set. We will come to another other rigorousness in the Fatou set. But the dynamics of the Julia set is quite a bit chaotic. So but just but we can still study some dynamics on the Julia set. So we will just focus on what we can have from the dynamics of the Julia set. We are not going to prove it, but it is based on some dynamics on the Julia sets. So, proposition. So let R C hat be a rational. Then So we have this. So what we can do, or we just study some amount of dynamics on the Julia set. After we iterate R on that Julia set, we will get the same Julia set. We will get the same Julia set. So it is enough to study the Julia set on R, Julia set of R, and that's fine, and that will give the entire Julia set. With the iteration, it doesn't matter from this. So this is a good thing about Julia set. And another thing I want to say is that another proposition. So let R from C hat to C hat, then total C hat, or this is another good thing about the Julia set. So if R a rational map from C to C, C hat to C hat, then Julia set of R is precisely the C hat, or Julia set of R has no integer. Okay, these are the two properties of the Julia set to study the dynamics of the on the Julia set. But we have seen that the dynamics is pretty chaotic here. So one thing I can just make a note is that you can to prove this or get some insight, you use Mandelbrot. We will state it. We will state it later for giving some insight about the rational systems. Another proposition. Let R be a rational map of degree then the number of critical points so R is the rational map, so which have a degree D. The number of critical points that R have is with multiplicity is 2D minus 2. You can show that. It is a very easy to showing that there is nothing. So by a certain transformation we can make, we have this. So from there we can use some, we can hit the definition of critical point that I had mentioned at the beginning of the talk. We will get RZ to be precisely B. Again we hit that same definition of the critical point. We get R prime Z to be minus alpha beta into So it comes out to be the degree is 2 dimensions. So again, using the definitions you can do, and emphasizing or hammering the fact that infinity is not a critical. Okay. So this is the the thing. This is very important, and I will talk something about this later. So another thing I want to make a comment on is that the Montel theorem that I have said. Suppose if family of holomorphic functions in the domain B of C hat omits 3 distinct points. A, B, C, then F is equicontinuous So this is the Montel's theorem, which says that F be a family of meromorphic functions defined on the domain B and omits exactly 3 distinct points from C hat. Then F is equicontinuous. So it is a very technical theorem. One can have a look. At the end, I will give some references. One can have a look for the proofs of all these. Can check it out. So another thing. So there is a lemma. After that we will give 2 big theorem. Any rational map. Or degree greater than 1 has infinitely many periods. Okay, we just give some transformation, change the coordinate, and we can give an existence of a periodic point. From that, we can have as many periodic points as we want. So there is a lemma. So this is the proof is very trivial. That is theorem that E and subtracting periodic point of a rational map, then if the basin of attraction A. So this basin is immediate. So immediate basin is what? Where in the connected component of uh, the component of the basin which contains that point. Okay. This is the immediate basin. We denote it by this contains a critical point. So what is telling that zeta is a attracting periodic point of rational map R. The basin of the immediate basin of the attraction. So what is the immediate basin? So the component of the basin which contains that point. That is called the immediate basin. Immediate basin of that point of that function A contains a critical point of that. So this is the basically this theorem basis. This is a very big theory. Now, in this regard, we have a good theorem which gives a bound on the critical points. Then I will move toward the dynamics of the Fatou sets. So theorem. So this is by the total number of attracting super attracting is point. So it's not earlier it was proved that this total number of attracting and super attracting points is 6 minus 6. That was done by Fatou. But recently this mathematician has discovered that and proved that the total number of attracting and super attracting fixed point of a rational map of degree is 2D minus 2. The proof is again very much technical. So we are not going to discuss it. So this is a bound. This is the most precise bound up to now. So this is a very good theorem. If you can appreciate it, it's very good because it somehow it giving us the idea about the how many roots that rational map from which the Newton map or the polynomial map F which corresponding to its Newton map F has this. So it is giving some idea. It's a very good theorem. And now we will just discuss the dynamics of the Fatou sets and some to introduce the Mandelbrot. And that will be good. So here we have our first theorem, which is Sullivan's no-boundary. So it says that the Fatou set of a map So what helps us? So whenever we have U, we have this Sullivan's no wandering theorem. So it tells that a Fatou set of a rational map has no wandering component. That is, if U is a Fatou component, so there exists a S such that this becomes period. So enough to study in this period what happens. Then we will study the total iteration. We don't have to go any extending to infinity. We don't need. We just do study the finite many sets, and it will be enough to know the dynamics on that factor. Okay. So pictorially we can have this. So this is the Fatou component U. We have R. This is R U. And so sometimes later, simply this is R third iteration. This is R four. This is R5. So U is the Fatou component. We have this R, we RE, and we go to R3, and we now keep rotating. Nothing is changing for some period 1, 2, 3, 4 times. After 4 times, it maps the same thing back again. So we just need to look what happens in this many sets 1, 2, 3, 4, 5, 6, 7. That will be enough to study whole Fatou component under this rational map. Okay, so this is the good thing on which we can practice. Now, so what you we for our convenience we take that U may be a simply connected domain. So for it is a simply connected domain. So simplest case that R3 is simply connected. Okay. So what we do, we map R3 U. We give 4 times iteration. We have this 4 time iteration R4, and we have landed over here, and we give a phi map. So what is the phi map? This is the Riemann map. And we get the disk. Okay, this is open disk. So we apply Riemann mapping theorem. This is the Riemann map. So we use Riemann mapping theorem, and we have this. Okay. So now we look this composition. It will from D to D. Okay. So what we have the simplest case for which this is simply connected. Now we applying Riemann mapping theorem, we can have that these are the conformally equivalent. But using this map, for being this is simply connected, we have Riemann map phi. We use this, it behaves similarly like this. These iterations. So what we reduced, to which we reduced is that a dynamics from D to D, a map from D to D, we check the dynamics. So it will be easy to check those dynamics rather than arbitrary simply connected. Okay. So okay. So what happens in the boundary? This is the open set. So what happens in the boundary is that maybe it is the Julia set. The boundary. And after just like that, we have the D on which is also the Julia set. So we need so the proper so we need something nice, so we find the proper holomorphic map. Which is image of compact set. Okay. So these proper holomorphic maps have this property to make the boundary will be will go to the boundary. So the Julia set will go to Julia set. So enough to study the dynamics on D closure. Okay. And we have what are the proper maps from D itself are the plus so the map will be just like or some rotation like this. So here you know, so A is that. So we have a map. So this is the proper holomorphic map. So proper holomorphic map from D to D at the precise the Grassley product. So this is the rotation. You can check it. So it's the application of maximum modulus. It is just an application of maximum modulus. So as far as what we have done is that we don't need to check the dynamics on that. We need to check the dynamics on the closure. It is enough to study the dynamics. Okay. Now we will take our today's one of the last and the most important theorem, which is called the Granger-Wolf theorem. If from D to D, then if is either a rotation rotation or basically says that if we have a so we have now P, we have P, then the iterations comes to somewhere maybe inside. It is just defined to be the rotation, and maybe after iterating this on this set D, we get all these converges to something inside or something anti-complementary. Okay, we will the inside and the complementary. We have so now. So this is already every periodic map periodic component is either same or fraction of attracting fixed point so attracting fixed point, for example, the case 0 is fixed point, or U is conformal equivalent B or this is the animals of this such that rational map restricted to U is this gives the complete classifications with respect to the basics. Okay, so that's why these theorems are the most important theorem to study the dynamics on the particles. Here, this is 2 pi I theta z and theta belongs to. So why we have taken that theta from the irrational? So one can emphasize this fact using that whenever we have the rational map, we just iterate it. If we take theta to be rational, after a certain stage of doing, so there exists a rational map such that when we iterate this map on over here, we get a integer point, so which will give the same point with which we have started. So to avoid this, we have to choose the point from irrational. So this theorem, the Mandelbrot theorem and its corollary, actually classifies the periodic Fatou components, how the periodic Fatou components look like, and a rational map act on that periodic Fatou component in which form it just classifies. So these are the two important theorems. So this is the up to this I want to discuss about the dynamics of the Fatou set. So I just introduce the Mandelbrot set and stop. we are taking as easy example. So what is doing? So we have a rational map Z R, and we pat out it with some C from capital C, complex number. Now we want to study how the dynamics behaves. So we have seen that the dynamics on the Fatou components and the Fatou sets are very nice. Now we just want to say, just want to know how it affects in the dynamics on the Julia set, because we already have seen that RZ itself has a very chaotic dynamics on the Julia sets. Okay. So we have this. We introduce this set, Mandelbrot set, but here I can't discuss it more because to study the Mandelbrot set we need some technical tools from ergodic theory and so to study the topology of the Mandelbrot set. But one thing we can emphasize is that it's not a domain or something. It's actually a parameter space. So why it is parameter space? We can vary C. We can vary C and check what happens in that in the dynamics of that rational map. So this is just the Mandelbrot set I want to discuss. One thing, the boundary of the Mandelbrot set is called the bifurcation locus of So we will see some picture after this, the theoretical part over. So we will see some picture to when that time I will illustrate that what is actually pictorial, what is happening. So all the motivations of doing all these stuffs is basically lies a thing which I need to just say is that one thing was that find the root. Now then one can ask that yeah, it's an algebraic equation and C is algebraically closed. Somehow we can find out the roots. That is not an issue. But if we have this type of equation, these are the polynomials Z. Okay. Here, no longer the fundamental theorem of algebra going to help us, because it is just a real analytic thing. It's not a polynomial in Z. It is consists of Z, Z bar and so on the term. So how would we solve these types of equation? So we can study the whole thing we have studied. We use these things to study this, and there is an open problem. Open. That what is the upper bound of the number of roots open question. So by studying the dynamics we can give an estimate about the number of roots these types of equation may have. So that's the motivation of studying all these dynamical systems and so on. So I want to just mention some references that you can look for knowing it further, and the proofs that I have skipped you can check it out. So I just write down the chronology. So there is a book called Holomorphic. on dynamical system. So you have to read it at once to get comfortable with real case. Then you can go to Beardham's book. After that you can visit John Milner's book, but it is advanced, little bit advanced. And fourth, one of the pioneer of this field is this guy. From Stony Brook. His notes. So this is the thing you can study. There is many papers available in the. It's an emerging topic of research today. So I just want to give some pictures of this to conclude my talk. So can you help to just? So here is some illustrative pictures that I have got some the note that last guys. So yeah. So what we do, we have this transformation. So z goes to 1 plus this and rational transformation. Observe that. And under this, the points on the Riemann sphere C hat goes like this. You can check it. So it's a nice picture actually. It's we just have this polynomial the rational transformation. We have this type of. So we are not going that much interesting here. So here is the we illustrate the Fatou and the Julia. So fz equal to z square. So basin at infinity is infinity. We have observed there. So here is the basin. Here the infinity basin. So all the points outside mod z equal to 1 blows up to infinity as when you iterate this net further. And the point strictly inside mod z equals to 1, it goes to 0. So these are actually the Fatou sets, and this is one Fatou component and this is another Fatou component. And we have observed that the z equal to 1 is the precisely the Julia set for the f equal to z square. So here and here we have z square equal to minus half. So here is the Fatou component here, and observe that infinity is another basin. So the point outside this thing goes to infinity, and inside the roots. So we just define the roots here. So that will make a Fatou. So these are the precisely the basins. So this boundary which we are denoted here is the Julia set for this. Okay. So this is just a pictorial view, understanding the Fatou and the Julia. Here is another z cube equal to this z cube minus 1. This is also a polynomial. So we just go to the Newton's method and we check that these are the attracting points. These are the attracting points, the greens and so on. But and these are the basins, precisely the 3 basins of z cube minus 1 and 3 roots here. But we can't say about this point. What is happening here? It is attracted by this set, or attracted by this set, or attracted by this set. We can't compute. So in these points, if we precisely can define the Julia set, we will see that these points come to the Julia set of this. Okay, and we know we can prove that for this the Julia set is have a positive basis. It's not a measure basis. Okay. And here is another. We just scaled z to be z square plus 1 or z square minus 1 and so on. We have just drawn. Now we have drawn this z square equal to minus I. We will have this as the Julia set. and these are the Fatou sets. So where infinity is the base. So we have these two nice diagrams. This is the just same thing which we have discussed. Yeah. So one thing is to ask that is it true that the Fatou components or the Julia components have some nice orientation or something nice, but it may not. It may be may not be a symmetric thing. It's a very totally disturbed thing you can observe here, where the Julia set is a kind of type. So here the picture we get is quite bit irregular. It's not a very nice or symmetric picture. That's why this is the which we can see in that picture. So this represents the Mandelbrot set. So here, if we change the bifurcate or pattern the rational functions a little more, nothing changes. Or maybe is in the changes are considerably small. Here is also the same, but on the Julia sets we have defined on the Julia sets it remains has the connected Julia set. So that on the boundary means this here it represents the chaotic dynamics here. The Julia set itself gives a chaotic dynamics. Now on that Julia set, what we do is we pattern the rational map a little more, and we see how the dynamics changes, how the dynamics show light. So this is the representation of this is happening actually if we draw it like this. So you can see that it's pretty irregular and it's pretty much chaotic. It's no regular shape. It's nice to see, but the study in these points, in these boundary points, is very much difficult and very much fine study is needed to study this. So I end here. So thank you for that. If you have any questions, you can ask.
Are there any questions? If not, then we thank our speaker again.